Okay, so let's look at the whole front. Are we sure the whole front? 64.
64, whatever. The first three.
First three. So I've got plus Q. You got 53 right, and you didn't get 52 right?
Yeah.
Holy monkeys, how'd that happen? Okay, so I've got an arrow, I've got an arrow, I've got an arrow, I've got an arrow going out. I have an arrow coming in, arrow coming in, arrow coming in, arrow coming in. I got an extra set of arrows like this. Agreed? I don't know, that's what it says. The picture says. I'm just drawing a picture. Did I do that picture right? So they say this is plus Q. So they ask, what is this thing here? Well, okay, couple things. First thing, are the arrows going in or out of this outer shell? In. So this is going to be a negative whatever. Okay. How many arrows are leaving this thing? 1, 2, 3, 4. How many arrows are hitting this thing? No. 12. 1, 2, 3, 4. 5, 6, 7, 8, 9, 10, 11, 12. So I have 3 times as many arrows hitting it, so it's going to be 3Q. The nice thing about this one is they didn't give a 2Q answer, which would have sucked everybody in because people miscount the 4 in the middle. Those are leaving and hitting. Don't miss class, Belay. Yes? Right, so these are all going in.
But I mean, like, positive has the arrow going out of itself.
Right.
Because they're coming in. Is the big blob the Q?
This thing in the middle is the positive charge. This circle on the outside is where the negative charges lie.
That's the charge?
Yes, where the negative charge lies. No.
I thought the charge was
If you see stuff going in and stuff going in, there's got to be charge in this, whatever this thing is. That's by definition. All right, let's do the one that Karis. Did you get? No, did you get the next one right?
No.
Darn it! You were the expert on this. I'm gonna have you be my expert.
I seriously sat there and I don't even know how I got it wrong.
So K 2Q Q over D squared, right?
Yeah.
The K and the D are going to be boring and irrelevant, so I've got 2Q squared K over D squared, agreed? Is my first force.
Okay,
2Q times Q, right? K over D squared.
Isn't it negative though?
Sure.
Okay.
Good?
Yes.
Okay, now roll them together. Bank. Roll them back apart. What's the charge in each one of these?
Well, wouldn't one be plus? Wouldn't one be neutral and one would be like a positive? No.
Charges continue to flow until they're equal, right? They're the same size?
So then they would both be positive.
Positive what?
1.
No.
No.
Half a Q.
Wait, what? Charge flows.
Charge is going to flow until all the charge is gone, and it's equally proportional on both of those conductors, right?
Right.
If I've got 2Q and negative Q, I have 1Q worth of charge once I hit them together, right? Half of it would go on this one, half of it would go on that one there. Agreed? Yeah. Okay. So now I'm going to redo my formula. KQ, 1/2 Q, 1/2 Q over D squared, right?
Uh-huh.
KD squared doesn't matter. I get 1/4 Q squared, right?
Yeah.
From 2 to 1/4 means 8 times growth. The only one with an 8 in it is E. Agreed?
Mm-hmm.
All right. 52. 52, I have a positive test charge here. Positive test charge here. First of all, did everybody read that correctly? A bunch of people see the minus over here, and they say I got a negative and a positive, and then the whole problem's wrong, guaranteed, from that point forward. They have a point here, which they call D, a point here, which they call E. A point here we're going to call A. We're going to call this one B. We're going to call this one C. Now, looking at this problem, the first thing I'm going to note is this. Is there any difference between D and E?
No.
Could they be the right answer to this question at all? No. Why do we even consider those? We're not going to consider those. They're a waste of time. I have 5 answers. I have to come up with 2 more. And they put 2 more on there. That's what happened there. So the question is, where is the electric field the least? Now, the first thought should be C. You should inspect this and go, C is clearly going to have the least amount of electric forces on it. The problem is this. At A, this charge is pushing that way. At A, this charge is pushing that way. What is the electric field at exactly the middle? 0. And that is the least. Because everywhere it's going to get pushed here and it's going to get pushed here, right?
How's big three?
All right, let's handle A first. You got that one. 53. That makes sense.
Sure.
Okay, so 52 makes sense. 52 is important. 52, everybody should get 52 right. Everybody should then get 53 wrong for using the same reasoning you're about to express. But has everybody got 52 right now? It makes sense to them. Can they do that? Okay. Now, voltage is what? Electric potential difference is what? It's the amount of energy it takes to get there, right? So I'm taking a positive test charge and I'm running it this way. If I'm running it this way, this requires, by the way, am I going uphill, first of all?
Yeah.
Of a positive test charge, would that be going uphill? Would it be fighting the forces?
Yes.
Yes. So this would be the least part of the hill. This would be higher. Now where things get interesting. There is no electric field here, right? In fact, it goes, if I put a thing here, it's going to roll this way. It'll even oscillate back and forth to get pushed from this guy, which is close to this guy. So it's going to kind of oscillate between these two. But in order to get to the spot in the hill, don't I have to go up here? So don't I have to keep pushing this in here? So isn't this going to require more work than just simply dropping it off here and leaving it here?
Yes.
So this, getting through here, is going to require more energy, right? So it's uphill this spot here, and then we have this little valley on the top. So if I was going to draw the potential difference, it would look something like this. Where this spot here is B, and this spot here is where the first charge is, and then I have the second charge. This is the middle. This is where A is.
Oh, okay.
So I have to go past, so I have to go more energy to get to this spot. At some point, we get it refunded, but I have to get up there first, right? And so it's how much energy it takes to get there. And because it's kind of rising the hill, I totally understand. Getting number 53 wrong doesn't make me sad even a little bit because it feels like, wait, it's got no electric field. How can it possibly be lower voltage? And the answer is you can't get there until you climb the hill to begin with. It may be a flat-topped roof, but you got to climb the hill to get there. And so it's got more voltage. Okay, that's nasty. That is, you know, the reason why that 52 is on here is because 53 is really nasty. But it's something they throw out every. This thing happens all the time. There's different variations of the same thing, but you'll see them all, and it'll be fun. So you really need me to do 40?
No.
Okay, double checking. There we go, 40. Next, you are with us, right? Because we're teaching stuff, right? We're learning stuff. I'm about to say test next time, and you'll be like, what?
Yeah.
Next time, what?
Yeah, test next time, what?
I like the back.
Okay, so on the back, what do you want me to do? Let's do E for certain.
No.
Anything else you want me to do? All the rest of them are right? Sweet. All right, let's do E.
Want anything on the back?
Let's do E. I've got two ways to do E. Two ways to do E. I'm going from 1 meter to 2 meters. I'm letting go of the charge. It's going to fly back that way. Agreed? So my positive test charge is over here somewhere. I've already isolated several pieces of this puzzle. Agreed? Now the question is, which way do I want to go? There is two actual ways to do this. There is one way, which would be what? Potential energy, right? If I was just looking at this problem for the first time without doing anything before it, I'd probably go potential energy. What's potential energy? KQQ over D squared, right?
Potential energy?
No, R.
Negative.
Negative R. Sorry, do it for us. Minus negative KQQ over R. Agreed?
Yeah.
Plug everything in. Negative 9 times 10 to the 9th. Q is equal, actually, you know what? I'm kind of being lazy here. That would be the potential difference between the two spots.
Yeah.
I should probably just do energy before energy after. Can I do that instead?
Yeah.
I
Yeah,
apologize.
that's
But I was on the right track. This will get you the right answer. I'm not really, cheating or anything. But I have potential energy at the beginning. I have potential energy plus kinetic energy at the end. Agreed?
Yes.
And so if I do potential energy at the beginning, I have negative KQQ over R is equal to negative KQQ over R plus 1/2 mv squared. Agreed?
Yeah.
Okay. So I've got negative. K is 9 times 10 to the 9th. I have Q1, which is 2. Q2, which is 4. Over the distance between them, which is 1 in my initial condition.
Yeah.
And then I've got negative over here. I've got 9 times 10 to the 9th. I've got the first Q, which is 2, the second one, which is 4, but now they're going a distance 4 away from each other.
Yeah.
Okay? Plus 1/2, the mass is 12,000 v
No,
squared.
it's 2 away from
Resi
each
is
other.
2, sorry, 2. Doing the previous worksheet.
That's twice as big. Times 2.
Oh, wait, shit.
Right? And then I can solve that for v. It's not for v. Yeah, for v, velocity. Shouldn't see v in this chapter. For speed. Agreed? So that's one way to go. The other way to go, we go, what's my voltage difference between those 2 points? So I could go the integral from 1 to 2 of the electric field, which is going to be kq over d squared, right? Let's make this an r squared, so we can say dr. Okay, so then I've got kq negative over r, agreed? Okay, from 1 to 2. Plug in a 2, and I get negative k. The charge that's in the center was the 2 Coulomb charge, right? That's not the one we're moving around. Divided by 2 minus.
We're moving around 4.
It's 4.
Right, so the one we're not moving around, the thing that making the electric field is the 2.
Yes. Okay. Yeah.
Okay, so that so then this is k times 2 over 1. Agreed?
Yes.
Okay, if I put that in my calculator, I'm going to get my voltage is equal to equal to 1.8, so 9 times 10 to the 9 volts.
No, but,
Okay, that's just voltage.
oh, okay. Yeah.
So how do I find the energy that I would have?
Multiply that.
So VQ. So if I multiply that by 4, I'm going to get 3.6 times 10 to the 10th joules. That's energy before. Set it equal to 1/2 mv squared. You get your answer. That looked unsatisfactory at the end. What do you got, Karis?
I don't know.
Okay, so this is my voltage, right? Here. Okay.
Yeah. Oh, yeah. No,
So I would go energy before equals energy after. I would go VQ is my energy before, and that's going to equal to 1/2 mv squared at the end. And then I'm just going to plunk everything in.
Yeah. No, I'm just trying to figure out what the hell I did.
Okay.
Because
All right.
I did the same thing.
Resi, you said the back would have been 4.
Way different answers. So. I don't know.
Okay. Well, if you didn't do your homework,